Good morning. Let's begin. This is Professor Grenfell with another lecture for Math 12 Statistics at Riverside City College. And today we're going to be discussing Chapter 3, continuing. And this is the third section. This is on measures of position. So first thing is the z-score. The z-score is one of the most important or most common usages of measurement of relative position within a data set. This is what we're going to be calculating almost all of the time. So I'm going to really hammer on this and say the z-score is the value from the distribution minus the mean from distribution, all divided by the standard deviation of the distribution. Okay, let's just abbreviate that. So for samples, the mean for a sample is denoted by chi-bar, and the standard deviation for a sample is denoted by S, and almost every single time the data value itself is just denoted by X. So that is what it would look like for a sample. For populations, what would it be? Well, for a population, the population mean is denoted by mu. For the standard deviation, we would call that the Greek symbol sigma. That's lowercase sigma for the standard deviation, not to be confused with the E-looking one, the uppercase sigma, which is for summation notation. And so here, and again, the data value is just X. So for a sample, Z is equal to X minus chi-bar. Notice that this is an X, and this is chi, with the bar over the top of it, chi-bar. And let's see, sorry, I left off. Oh, and that's divided by the sample standard deviation, so that would be S. For a population, Z is equal to X minus mu over sigma. But that is how we will compute the z-score all of the time. No matter what distribution that we're looking at a value out of that distribution minus whatever the average is for that distribution, and then we're putting that in terms of the number of standard deviations away from the average that is. And so that is where the standard deviation comes in the formula. We have to divide by the standard deviation. Okay, so let us take a peek at example 3-27. I'm looking at page 147 from the textbook, and this is talking about test scores. And I've gone ahead and kind of just skimmed the problem. It says compare relative positions on the two tests, okay? So here, what we're going to be doing is we're going to be calculating a z-score for each of these. This is our first measure of relative position. And so for the z-score, we have to know what? Three things: the value, the mean, and the standard deviation. So for this example, as I'm reading through this, I want to keep track of what is X, what is, well, we call the mean either chi-bar or mu. So depending on what the particular case is, whether it is a sample or a population, we have to determine what that is, the mean. And then again, do we call it S or do we call it sigma? It doesn't really matter because we need to know what it is because we have to divide by it. And what it is going to correspond to whether it's a sample or whether it is a population. Okay, so let us go ahead and read the setup. It says a student scored 85 on an English test, while the mean score of all students was 76 and the standard deviation was 4. She also scored 42 on a French test where the class mean was 36 and the standard deviation was 3. Compare relative positions on the two tests. Okay, so I have gone ahead and reorganized my initial framework. We have two different tests, an English test and a French test. And here I'm going to say that these are samples because this English teacher, they may give the test thousands and thousands and thousands of times for different semesters or different sections of the same class, and same with the French. So this is just one particular class's test, and we're just looking at the class averages and trying to compare their scores, French scores and English scores. Not the same test, and so the scores are not the same. But we can compare how well this student did with respect to their various different classes individually on the on the whole by using their standard score or the Z-score. So let's just copy down the information. For English, their test score was an 85, while the class average was 76, and the standard deviation was 4. Okay, and then for the French exam, they scored a 42. The class average was 36, and the standard deviation was 3. So notice here, they both scores were above average, right? So we can't just look at the individual score itself, okay, and say, oh, look, well, an 85 is better than a 42. We don't know that because it is dependent upon how much the test was out of. Or in general, if they're going to grade on a curve and normally distribute the grades, and then you would say, well, okay, look, the one's higher than the other, so there you go. We can't necessarily say that without considering what is the average. And notice in this case, she scored above average. Her score X is greater than the mean, chi-bar, in both classes. And again, you can't even say, well, she did the same because she was above average. That's not fine enough distinction. And so what we need to really do is bring the standard deviation into that. If we can say, well, she was 1 standard deviation above the mean in her French class, and she was 7 standard deviations above the mean in her English class, then she obviously did a lot better in the English class. She did better than average in both of them, but in the English one, she was so much higher above the average because the Z-score was greater. This is how we can compare two different samples or two different populations that are not coming from the same set, that are measuring two different things. We can still say their Z-scores are comparable. They're standardized scores in that sense. All right, so the Z-score for this one, Z is going to be equal to X minus chi-bar, all divided by S. Notice I am practicing good practices here. Anytime I need to utilize a formula, I'm just reciting it from memory. And it's a means of making us memorize it, right? But it's not just pointless memorization. We're memorizing it when we need to use it. So we're recalling it. So this is very nice. All right, so this is 85 in place of X, minus 76 in place of the class average, all divided by 4. So we'll work this out. Okay, so here we plugged in 85 minus 76, all divided by 4, punch that into the calculator, we get reduces down to 9 divided by 4, so the Z-score for the English exam is 2.25. And then similarly, we're going to plug in 42 in place of X, minus 36 in place of chi-bar. This is for the French test, so it's a different sample, different mean, all divided by 3, different standard deviation. So we simplify this, and so this reduces down to 6 divided by 3, and the final result is 2.0. Okay, so for the English test, that, let's say that mark right? That grade of 85 when the class average was 76 and the class standard deviation was 4. That Z-score worked out to be 2.25, right? And for the French class, the test, the score that she got on that, had a relative position of 2.0. So I hate doing this in the regular lecture just because it takes so much time. But on the video, I can stop and write all this stuff and then unpause. So here, in conclusion, since the Z-score for the English class was a 2.25, and that's more than 2.0, that was her Z-score on the French test, her relative position for that test value, she got relatively better on the English test than she did on the French test. So essentially her progress with respect to the rest of those two individual classes was greater in English than it was in French. Okay? So that is how we can compare two different things that are not related to one another. So again, the English test, the French test, they could have been out of two different numerical values. Looks like maybe the English class was out of 100 and the French test was out of 50. Okay, so we can't compare the scores directly. We can't even say, well, the average here was this and the average here was that. We also have to take into account how far spread out. I was trying to think of the word for how varied the data is. I guess that's it. Right? How far spread out the data is, because the scores in the English class were a lot more dispersed, right? A lot more spread out. Even if she was above average, she'd have to be a greater distance because that standard error, that standard deviation, was greater in a more spread out, let's say, more widely varied data set. Okay, let us continue on to another example looking at relative position in order to compare two different samples that are coming from two different populations. So here we're talking about marriage ages. In a recent study, the mean age at which men get married is said to be 26.4 years, with a standard deviation of 2 years. And the mean age at which women marry is 23.5 years, with a standard deviation of 2.3 years. So then it asks us, it says, find the relative positions for a man who marries at age 24 and a woman who marries at age 22. Okay, so here it has given us all three things that we need: the mean of the distribution, the standard deviation of the distribution, and a certain data value from within the distribution for each of these two samples. So each of these two samples has a different distribution, and so we're going to be looking at where within this distribution, where is this X value, and how does that compare to its relative position within the other distribution. So that is what we're doing by computing and then comparing Z-scores. Don't forget, write down the formula, the equation that we're going to be using, so that a Z is equal to X minus chi bar, all divided by S. And then we plug in 26.4 in place of chi bar, 24 in place of X, and 2, of course, is going to be in the bottom. And notice here, I did it the wrong way. Oops. I plugged in the X and the chi bar switched up. The key indicator here, I didn't show the scratch work, but when I was looking at this, I got a positive Z-score. And I said, wait a minute, this man is younger than the average age. their z-score can't be positive. His age is lower. It has to be a negative z-score. So that was one way that I caught myself and kind of messed up, but then figured it out and caught the mistake and fixed it. So previously I had gotten 1.2. So yeah, 26.4 minus 24 is 2.4, and then divide by 2, that gives us positive 1.2. And I said, wait a minute, that's not right. And so to fix it, notice it's going to just be negative, but the same absolute value. Yes, so the z-score for this man's marriage age is negative 1.2. Then for the woman, her z-score is, again, notice I just repeated the formula, z equals x minus chi bar, all divided by s. So substituting n, of course, correctly this time, so it's x first, so 22 in place of x, then 23.5 there in place of chi bar, divide by 2.3, and that works out as negative. Again, that is correct because her age is lower than the average age of marriage for women. So there it is right there, negative 0.65. And so in summary, since the man's z-score was negative 1.2 and the woman's z-score was negative 0.65, notice his z-score is roughly twice what hers is. So they both married young, relatively speaking, compared to the average, right? But the man, his z-score was lower, and so he was younger than the woman, comparatively speaking. So the man married young, the woman also married young, relatively speaking, but the man married at a younger age with respect to the average age for men and their standard deviation than did the woman. Because his z-score was lower, that's what we can say about this. So here, 22 compared to 24, it turns out 22 is actually higher for a woman than 24 is for men. Strange.